Hello. So in part one of this video, we looked at this process of the sliding filament theory and saw how actin and myosin, these proteins within your cells, are able to cause shortening of these sarcomeres and therefore your entire muscle. And you may recall that whole process started with the release, kind of the sudden appearance, I should say, of calcium, which kind of enabled that whole thing to happen. So the question then for now, this next part, is where did that calcium come from? Well, let's figure it out. To look at that, we need to zoom in on an area called the neuromuscular junction. And you have this picture in your study guide packet if you wanted to reference it, draw on it, whatever. But the neuromuscular junction is the region where the neuron, which is this, contacts the muscle. In other words, where the nervous system tells your muscle, hey, it's time to move. So if I want to bend my arm, my brain is telling me to do that. This is where that happens. The neuron is talking to the muscle right here. So the question is, how does it talk to it? There's three players, and then we'll look at the process. Player number one is a neurotransmitter called acetylcholine. And acetylcholine is located in these what are called synaptic vesicles. You may recall those from when we looked at neurons. This is a neurotransmitter that works in the neuromuscular junction. In other words, it goes between the neuron and the muscle cell. Then you'll notice that the muscle cell has these infoldings of the cell membrane or sarcolemma, and those infoldings are called the transverse tubules, or sometimes they're just called the T tubules. And so those are these infoldings of the cell membrane. And then finally, the sarcoplasmic reticulum is this structure here labeled 3. And that, as you may recall from previously, that stores calcium ions. So how does this all play out? Well, step one is when you decide, hey, I'm going to move my muscle. Your nervous system sends a signal down the neuron through a series of action potentials, just like we learned about before. And when it reaches the synapse, it causes the synaptic vesicles to release acetylcholine into that synapse. And just like with neurons, the acetylcholine is going to bind to receptors on the cell membrane of the muscle cell, and it's going to trigger an action potential in the muscle cell. Now, when I was first learning about this, it really bothered me for some reason that muscles could do action potentials. I always thought action potentials only happened in neurons. Turns out, no, they can happen in muscle cells as well. So basically, just like what happens in a neuron, we have an action potential. And so then this action potential is going to cause another one, which causes another one, which causes another one. Again, just like we learned about before, causes another one. But then something interesting happens. The action potential follows the membrane as sodium ions rush in, potassium ions rush out. And since it's following the membrane, it's going to end up going down the T-tubule system. So it comes all the way down, exponential, 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 exponential. And when it reaches the sarcoplasmic reticulum, that causes the sarcoplasmic reticulum to release calcium ions. Those calcium ions then are going to initiate the sliding filaments in the way we discussed in part one of this screencast. The calcium binds to troponin. That shifts tropomyosin out of the way, revealing these binding sites for myosin on actin. That allows the myosin head to attach. The myosin head bends, sliding that filament. ATP allows it to let go, and then this process repeats over and over and over. So that's what causes that sliding of filaments. And so what's amazing now is this takes us back to this little flow map that I introduced, what, a month, 2 months ago? I don't even know when, a long time ago, where I started throwing tennis balls at you guys. We said that in order to catch a tennis ball, you need sensory input, integration, and motor output. And we've now delivered. We began by looking at the brain and the nervous system and how action potentials and synapses send signals around the body. We then backed up and looked at how the sense organs were able to take signals from the environment and convert those into messages that the brain can understand. And now we understand how the nervous system sends signals to your muscles and causes the muscles to contract, and how those muscles pull on bone to generate movement. Sensory input, integration, motor output. Is that amazing, children? That's amazing. I hope you're impressed. That's pretty cool. We've done a lot of anatomy so far already. So, whoops. Yeah, did all those. Okay. So, since we're so excited, I thought I'd bring us back down with a not-so-fun fact and talk about sarin nerve gas. You may have heard of sarin nerve gas. In 2017, Syria, their leader Bashar al-Assad used nerve agents against his own people during the civil war. Or you may have seen, nerve gas in movies, or maybe just have heard in social studies that nerve gas is bad and we don't want to use that. And so what's up with nerve gas? What's the big deal? What's it doing? Well, it turns out that sarin nerve gas acts at the neuromuscular junction. So here's the typical situation that we just discussed. When your brain, this is the neuron here, when your brain sends a signal to your muscles, it causes the release of acetylcholine. Acetylcholine binds to the muscle and eventually causes that muscle to contract. Now think back to when we studied neurotransmitters in the nervous system. What should happen to acetylcholine after it's done its job? And hopefully you're thinking it had to leave the synapse, right? And we said there's two ways it can happen. It can leave the synapse through reuptake channels and go back to the original cell, or an enzyme could just destroy it. Well, in this case, it's an enzyme that destroys it. So there's an enzyme called acetylcholinesterase. I played that in my Words with Friends game and got 2,817 points. That was pretty cool. But this enzyme will bind to acetylcholine and destroy it. And then your muscle relaxes and all is well again. So that's what's normally supposed to happen. Neurotransmitter is released, sends its message, and then it's destroyed. It doesn't do any more. Well, in the case of sarin nerve gas, what happens is sarin basically inactivates that enzyme. If it inactivates that enzyme, acetylcholine isn't destroyed and it stays in that synapse longer. And you may recall when we talked about cocaine, we saw that cocaine has the same effect with dopamine. It keeps dopamine in the synapse for too long, and that's what causes the high. Well, in this case, acetylcholine is in the synapse too long, and instead of causing a high, it's overstimulating your muscle. And that is why this is such a horrific thing, because your muscles are involved in everything. And so someone who's exposed to this is going to have this uncontrollable muscle spasms as they kind of jerk and shake their whole body. But then it gets even worse because remember, your muscles are involved in breathing. You have this diaphragm below your lungs. That muscle goes into spasms. Your entire digestive system is smooth muscle. That goes into spasms. And so you can get involuntary urination, defecation, drooling at the mouth, foaming at the mouth, and then even your heart is cardiac muscle, and that goes into spasms, and that's what eventually kills the person. And so you can understand why this is such a nasty thing. By keeping that acetylcholine in that synapse for too long, it causes that overstimulation of muscle, which is not a good thing. So this has been a lot. This is a complicated topic. I really, really, really recommend that you pull up the notes on Schoology and watch this animation. This animation does a fantastic job showing this in kind of 3 dimensions. You can just kind of watch it all happen, and it is well worth the few minutes that it'll take you to pull that up and watch it, because it really does tie this all together nicely. So hopefully you understand how your muscles work. Every time you bend your muscle, it is because of these sliding filaments sliding past one another, and the collective action is pulling on those bones and causing them to move. And if you're not amazed by that, just think about it some more, because you will be when you get it. Here's finally 2 TED Talks, totally optional, but if you're interested in checking those out, those are kind of cool too. So that's it. This homework 5C is going to be another day's assignment, so you're welcome to get a jump on it, but it won't be due for a little while just yet. Thanks, everybody.